Welcome to the practice assignment session for the course content covered in week 12. So, this is the last week of our problem solving sessions. And to begin with, initially we were seeing reviews of various lectures, and then we stopped with around, I think, lecture number 36. After lecture 36, you had seen about optimum power allocation, the different spread spectrum techniques, the direct sequence spread spectrum technique and the frequency hopping spread spectrum technique, the properties of spreading sequences, then introduction to CDMA, basically the code division multiplexes, and what are the different features of CDMA 2000 and WCDMA. And then you saw about rake receivers, and then multi-user CDMA detectors. Then I think in the last week you would have seen about the basic understanding of MIMO systems and then the system capacity. So these were the various topics you had seen in the recent 3 weeks. Uh, so let us begin with the problem solving session. Question 1. Why is CDMA a sensible case for deployment in rural areas? Options: as the number of cells is fewer, other cell interference will be less. Coverage area can be increased for lower load cases. Both A and B, neither A nor B. What's the answer of this? So the answer is both A and B. As the number of cells is fewer, other cell interference will be less, and coverage area can be increased for low load cases. CDMA is primarily limited by interference. So, in rural environments where the base stations are further apart than in urban scenarios, CDMA systems encounter less interference from adjacent cells and thus perform well. So, if we see the signal to interference noise ratio EB by I naught plus N naught, here our interference will be less because the base stations will be far apart. In low load cases where the interference is like very small, thus when interference is small, obviously we'll be getting a larger SINR. So for such situations, system can handle less signal power. This means that the coverage area of the base station can be increased. So when the interference power is less, it means that we need a lesser signal power to achieve the required SINR. Hence, we could, so hence if we're given a particular signal power, we could increase the coverage area of the base stations. So the answer is both A and B. Which of the following is valid for power control? Power control is capable of compensating for the fading fluctuation. Received power from all the mobile stations are controlled to be equal. The power control mitigates the near-far problem. All the above. So, which of the following statements are true when it comes to power control? Yes. The answer will be all the above. So power control is capable of compensating for the fluctuation, and with power control what we're trying to do is the received power from all the stations should come to the base station like almost with equal power. So when this happens, the near far problem will be mitigated. So the answer is all the above. Okay. Consider a base station which communicates with two users and it uses two spreading codes C1 1111 and C2 1 minus 1 1 minus 1 for user 1 and user 2 respectively. So to communicate with user 1 we use code C1, to communicate with user 2 we use code C2. The multipath channel is given by h of n is given as zero point 0.8 and minus zero point 0.6. If the base station transmits the signal x of n equal to C1, what are all the correlation coefficients of the received signal at user 1 and user 2 receivers with their corresponding spreading sequences? So whatever you're sending, that signal is C1. It's passing through the channel and then you're receiving. So now what we are asked to find is the correlation coefficients of the received signal at user 1 and user 2 receivers. So how do you approach this problem? Okay, so let's see how to solve the problem. What we are sending is C1. So C1 will pass through the channel H of n and then it will be received. So the received signal will be 1111 which is convolved with zero point 0.8 and minus zero point 0.6. So basically if you try to do convolution with 1111 and zero point 0.8 and minus zero point 0.6. So it will be 0.8, 0.8, 0.8, 0.8, minus 0.6, minus 0.6, minus 0.6, minus 0.6. So we're doing convolution. So you just have to look like this. So it will be 0.8, 0.2 and then 0.2, 0.2 minus 0.6. So the received signal what we have is 0.8, 0.2, 0.2, 0.2 and minus 0.6. But what we will be receiving is, since we sent only a 4-bit sequence, we will be receiving only 0.8, 0.2, 0.2, 0.2 for now. So correlation when we are finding, we'll find with only these 4 samples. So same way you have to correlate with the received signal with your spreading code C1 in the first case to find the correlation with respect to user 1, and then for correlation with respect to user 2 with the received signal you will have to correlate with the second spreading code 1 minus 1 1 minus 1 transpose. So the answer what we are getting is 1.4 and zero point 0.6. Answer is option B. Okay, moving on. Which of the following are disadvantages of a CDMA system? Time synchronization is required, can result in several handovers, CDMA requires a tight power control, all of the above. What do you think are the disadvantages of CDMA? So the answer is all the above. Time synchronization is needed because it is critical to ensure orthogonality. So at t is equal to 0, like all the codes should be time aligned. That's very important. Second thing, as a sum of the power received and transmitted from a base station needs constant tight power control. This can result in several handovers. So we saw that to avoid the near far problem, we need to have a tight power control with respect to CDMA for it to perform well. So when you need a tight power control, obviously you're going to end up in handing over, resulting in several handovers. So all the three are the disadvantages of a CDMA system. Okay. Consider a 8 PSK transmitter where all the symbols are equiprobable. What is the entropy of the source in terms of the number of bits per channel used? So we have a 8 PSK transmitter. We are finding the entropy of the source in terms of number of bits per channel used. So let us see the answer. What's the formula for entropy? What's entropy? Basically, the measure of uncertainty. So the formula for entropy is minus summation I is equal to 0 to k pi log of pi. Sorry, actually pi should come within the inside the summation itself. So this will be equal to minus 1 by k summation over I is equal to 0 to k log 2 to log 2 into log 2 of 1 by k. Here we are replacing p by 1 by k because that it's given that the symbols are all equiprobable. So what we so minus log of 1 by k can be written as plus log of k. So you get 1 by k into the summation leads to k. So k log of k. So the answer is 3. If you put k is equal to 8 for PSK, the answer is 3. So there's another typo here. So this will be from I is equal to 1 to k. Sorry for the typo, guys. So solving this is like first you find write down the formula for entropy, find what's pi, and then you get to the answer. So the answer is 3. What is the entropy in the above problem if 3 out of the 8 PSK symbols are transmitted 5 times as frequently as the other 2 symbols? So it's like 3 out of the 8 are transmitted 5 times more with more probability. So how does your entropy formula change for this question? Okay. So let's see how to approach this problem. Let the probability of the more frequently occurring symbols be given as Q. So 3 out of 8 symbols, right? The probability for them is Q. Let the probability of the less frequently occurring symbols is P. So the other 5 out of 8 is P. And by the question, it's given as Q is 5 times P. It's 5 times more probable. Now we know that the entire probability, the sum of the entire probabilities should be 1. So 5P plus 3Q is equal to 1. And we know that Q is equal to 5P. So we get ultimately P is 0.05 and Q is 0.25. So after finding P and Q, now the summation will change as follows. So you basically split the summation with respect to P and with respect to Q. So we have 5 times whatever that comes with respect to P. So P into log of P minus 3 times whatever it comes with respect to Q. 0.25 into log 2 of 0.25. So the answer is 2.58. So option C is the answer. Okay. What is the entropy of real Gaussian random variable with mean mu and variance sigma square? Try to find the entropy for a real Gaussian random variable. Try the probability density function and try to solve it. Okay, let us see how to approach this. What is the PDF of real Gaussian random variable? The mean is mu and variance is sigma square. So P of x is 1 by root of 2 pi sigma square e power minus x minus mu the whole square by 2 sigma square. So this is a PDF. What is the formula for entropy? Minus integral minus infinity to infinity P of x log to the base 2 of P of x into dx. So try to substitute P of x into this formula, and then since you have log to the base 2 and then you have an exponential, you can it gets opened up, and just a simplification process, and you get the answer to be half log of 2 pi e sigma square. So the entropy of a real Gaussian random variable is half log of 2 pi e sigma square. Option B. In a MIMO scenario with NR receiving antennas and NT transmit antennas, and the channel matrix H is full rank. So they've given that we have NR receive antennas, NT transmit antennas. The channel matrix H is full rank. What is the rank H? It's also given that NT is greater than NR. So the answer will be NR. Let's see how to get to this answer. So the scenario, whatever we are considering, is that if H is known at the transmitter, that is, if we know C as IT, then we could do some kind of a pre-coding, which is H inverse into X. If this is taken as X tilde, that is what we transmit. So Y will be H into X tilde plus N. And we know that X tilde is H inverse into X. So what we get is Y is equal to X plus N. However, if H is not a square matrix, that is if H has dimension NT cross NR, then how does it work? So what will be the rank of H? If we consider the singular value decomposition, any rectangular matrix A of dimension n cross m can be written as U into sigma into V Hermitian, where U and V are both unitary matrices. U is a unitary matrix whose vectors will be u1 to un, and these will be the n left singular vectors of A. The left singular vectors of A can also be is also the eigenvectors of A Hermitian. And the unitary matrix V has m columns V1 to Vm, and they are called as m right singular vectors of A. And this will be the eigenvectors of A Hermitian into A. And sigma will be a diagonal matrix of entries from sigma 1 to sigma L. So what is the dimension L here? So it is basically the rank of the matrix H, and the rank of the matrix H will be lesser than or equal to the minimum of NT, NR. And here the assumption is H is full rank, and we know that NT is greater than NR. So minimum of the two will be NR. So the rank of H is NR. Okay. Moving on. Consider a matrix A which undergoes singular value decomposition as A is U sigma into V Hermitian, where sigma is a diagonal matrix of dimension n cross m and is full rank. It is known that n is greater than m. What is the structure of sigma? So we are given that it's a full rank. It is of full rank, and n is greater than m. Basically, the dimension of sigma is n cross m. So now what will be the structure of sigma? First, find the rank. What will be the rank? And based on that, how we could express sigma. Okay. So we know that A is U sigma into V Hermitian, and sigma is a diagonal matrix. So if you have a situation wherein n is lesser than or equal to m, then the rank will be n. So it will have n sigma 1 going up to sigma n, and the rest of the columns will be zeros. However, if you have n greater than m, The rank is m. So sigma can be expressed as sigma 1 to sigma m. So that will be a diagonal m dimensional diagonal matrix, and then the other rows will be 0. So the answer is A. Moving on to the next question. What is the log dead capacity of a channel given by channel transition matrix H? Here, given that there are more transmit antennas than receive antennas. So NT is greater than NR. That is the situation. And sigma x square is the energy of the signal and sigma n square is the noise energy. So we are supposed to find the log dead capacity, and it's given as the number of transmit antennas are greater than the number of receiving antennas. Okay, so let's see how to get a solution. Answer is option A. I'll try to give a very brief explanation of the entire process, how it goes. Okay, so in a MIMO system, now we have y is equal to hx plus n. Y is of the dimension nr cross 1, h is of dimension nr cross nt, x is of dimension nt cross 1. So nt is the number of receiving and transmitting antennas, and nr is the number of receiving antennas. What we are finding here first is mutual information. So mutual information is entropy at the output minus entropy of y given x. So entropy is what we saw was entropy is a measure of uncertainty. So if we want to find h of y given x, we can express it as h of, for instead of y we can write hx plus n given x. So now you have two terms, hx given x plus n given x. So given x, there is no uncertainty in hx, right? So directly h of y given x gets boiled down to h of n given x, which is again same as h of n. So there is no information what you can get from the data about noise, right? So h of y given x is directly h of n. So we have h of y minus h of n. We already know that h of x is log to the base 2 of determinant of pi e into rx. Substituting for h of y and h of n, we get log to the base 2 of determinant of pi e ry minus log to the base 2 of determinant of pi e rn. And trying to bring out the constant terms, we get log of pi the whole power n. Okay. The other important thing is here we know that nt is greater than nr. So what is the dimension of y here? If we think the determinant of pi e ry, it will be nr. So log to the base 2 of pi to the power of nr, e to the power of nr, determinant of ry, and the same thing, and there you have determinant of rn. Now we're going to find what is Ry and Rn. Ry is expectation of y into Y-hermitian, which can be written as expectation of Hx plus n into Hx plus n Hermitian. Now splitting their terms and the two cross terms which are going to go to 0, we get H into expectation of x into x Hermitian will be Rx into H Hermitian plus Rn. So this mutual information term gets boiled down to a very interesting form. So log to the base 2 of determinant of Ry by determinant of Rn is what we had. So it will be determinant of H Rx H omission plus Rn divided by determinant of Rn. Now this expression we could write it like okay, now if we have to find capacity, we can express ergodic capacity as C by B equal to expectation of this entire term. So expectation of log to the base 2 of determinant of H Rx H Hermitian plus Rn divided by determinant of Rn. Now this can be taken to the numerator, and if we split the terms, we get expectation of log to the base 2 of determinant of sigma x square by sigma n square into H Hermitian plus its identity matrix of dimension nr. So the answer is option A. So basic thing is we have number of transmit antennas greater than number of receive antennas, and here the determinant will thus be limited by nr. Now if you have to find the same thing with more number of receive antennas than transmit antennas, how is it going to change? So the dimension is going to be int. That's the main change. And you will get H Hermitian H. So the answer is option B. It's in a similar format. We'll have to work it out. So you guys can try it. In which of the following diversity cases would you see diversity gain but no array gain? So we'll have diversity gain, but we won't have array gain. Is it receiver diversity, transmit diversity, both A and B, or receiver diversity, the diversity gain and array gain are the same things? The answer is transmit diversity. So in transmit diversity, we'll have diversity gain but no array gain. We've seen this thing already. Okay. Which are the valid properties of H Hermitian? So we have a matrix H Hermitian, right? What are all the valid properties? Dimension of the matrix is nr cross nr, or is the dimension nt cross nt? And is it a positive semi-definite matrix, or is it only a positive definite matrix? Both A and C, or B and D? What is the answer, guys? So the answer is both A and C. We know that the dimension of H matrix is NR cross NT. So H-hermitian's dimension will be NR cross NT into NT cross NR. So it's going to be NR cross NR. And there are a few other properties I wanted to share. So H-hermitian, we know that it's by nature a Hermitian matrix. And H-hermitian is a positive semi-definite matrix. The eigenvectors, whatever we have, are all real valued, and lambda I is greater than or equal to 0. So these are the properties of positive semi-definite matrix. And if lambda i's are the non-zero eigenvalues of H-hermitian, they are the non-zero eigenvalues of H-hermitian H also. So these are few properties of H-hermitian matrix. Okay. The last question. Statement 1. At high SNR, the capacity of NT cross NR IID Rayleigh fading MIMO channel with full rank with CSI is approximately equal to N min into log to the base 2 of SNR plus K, where N min is minimum of NT and NR and is for some constant K. Statement 2 is, at low SNR, the capacity of a NT cross NR IID Rayleigh fading MIMO channel H with receiver CSI is proportional to SNR into log e to the base 2. Which of the following statements are true? Or whether both are true or both are false? So the answer is both the statements are true. Let's see how. With CSI, we use water filling and compute the capacity. So capacity is C is equal to summation I is equal to 1 to NR log to the base 2 of 1 plus Pi sigma I square into rho bits per second per hertz. At high SNR, we know that Pi can be written as P divided by NR for all channels. So for all channels, Pi is going to be P divided by NR. Thus, the capacity equation becomes summation I is equal to 1 to NR log to the base 2 of sigma I square into SNR. Now this becomes NR into log to the base 2 of SNR plus a constant K. So statement 1 holds true. Now if at lower SNR what happens is we have only one of the one channel and the power of that will be P and the others will be 0. Therefore, capacity will now become log to the base 2 of 1 plus sigma 1 square into SNR. This can be written as log to the base E into sigma 1 square into SNR approximately. So both the statements are true. So we've come to the end of the session. Thank you guys.